Hi, everyone. We're going to do an optional section now, but it's really cool stuff. Trig and Euler, or exponential forms of a complex number. So in the beginning, we were talking about a complex number, z. It was a plus bi, standard form. A and b are real numbers. Instead of a and b, let's use x and y, right? So here's standard form for a complex number. Z equals x plus yi. Remember, x is our cosine of theta, y is our sine of theta. We got that from earlier in chapter 6, in 6.3. So z equals r cosine of theta, that's x, plus y is r sine of theta times I, right? Factor out an r, z equals r times, okay, cosine of theta plus, bring up the I sine of theta. And you trig students, those of you who had trig, may remember that cosine of theta plus I sine of theta is sometimes abbreviated as CIS of theta. By the way, this is offered in a handout, both my notes and in a supplementary handout that I had. Okay, A or X is R cosine of theta, B or Y is R sine of theta, right? Okay. R is sometimes called the modulus. Theta is sometimes called the argument. Okay, R is from the Pythagorean, right? Theta, there's a tangent relationship. So it's a lot like 6.3, okay? Again, I have a supplementary handout on my website with this stuff. But again, back in Math 104, you may recognize we have R CIS of theta, okay? And it turns out that CIS of theta is in fact e to the I theta. And in just a moment, I'm going to show a video from Khan Academy that's going to show this. All right, that's the Euler or exponential form of a complex number. But I'll do that after the recording because I don't know what copyright issues there might be. So basically, here is standard form in Cartesian, z equals x plus yi, where x and y are real. All right. Here is polar or trig form, z equals r, basically CIS of theta. And then the exponential form or Euler form looks like this, z equals r e to the I theta. Now, the fact that these are equal, the Khan Academy video will show you why that is. It gets pretty deep. You're not required to know why, but it's pretty deep. It leads on to Calc 2, Calculus 2 on series. All right. Now, one implication for this, well, there are several implications. For example, you can multiply complex numbers very quickly, in a sense. If all you care is the values for r and theta, the modulus and the argument, what if we multiply two complex numbers? Ordinarily, you'd have to take guys like these and FOIL, right? Like 2 plus 3i and 4 plus 5i. You FOIL and you work that out. It wasn't too bad. But right off the bat, what you can do is in trig form or Euler form, if you multiply two complex numbers, you multiply their r values to get the new r value, and you add the theta values to get the new theta value. The reason is if you multiply two complex numbers, basically the r values multiply, and it comes from the rules for exponents. Remember, when you multiply powers of e, you add the exponents. That's why you add the arguments. So it comes through algebraically. All right. In general, okay, if you just care about these moduli and arguments, right? Basically, the distances from the pole, this is called the pole now, the pole or origin, the distance from the pole or origin, and this argument or direction angle, all right? Okay, when you multiply two complex numbers, you multiply the r values to get the new r, you add the theta values to get the new theta. For division, divide the r values, subtract the theta values. For powers, you raise r to the power, you multiply with the theta. Roots are more interesting. And in fact, I'll show you something really cool with roots. All right, let's look for a blank sheet here. Where can I get a blank sheet? Okay, so I'll get a blank sheet here. All right, over here, the blank sheet. So let's talk about solving complex equations. All right. Let's say that we wanted to solve z to the fourth equals 1. Basically, what are the fourth roots of 1? If you consider all complex numbers, what to the fourth is 1? What to the fourth is 1? Well, we have some easy answers. 1 to the fourth is 1. Also, negative 1 to the fourth is 1. We have two imaginary values that work out. I to the fourth is 1. And negative I, all to the fourth, is 1. And looky here. They form the corners of a what? These guys form the corners of a square. We have rotational symmetry. You go around 90 degrees. Every time you multiply by I, you rotate by 90 degrees. And you can verify that from the Euler forms. It's because I corresponds to a 90-degree angle. When you multiply by I, you keep adding 90 degrees to the argument or direction angle. Now, in general, what if I consider, how about this? What if I had considered, let's see here. What if I consider z to the fifth equals 1? All right, okay, z to the fifth equals 1. All right, so we consider z to the fifth equals 1. What are the fifth roots going to look like? Well, 1 to the fifth is 1. And this time, we're going to form not a square, we're going to form a pentagon. So here's the first fifth root, second, third, fourth, fifth. Remember, okay, if we subtract 1 from both sides, we get a fifth degree polynomial with real coefficients. This guy has how many complex zeros or roots from the fundamental theorem of algebra? This guy has 5 complex zeros, just like this guy had 4 complex zeros. Boom, 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 right? Well, z to the fourth, if you write this as z to the fourth minus 1 equals 0, right? We have 4 complex zeros or roots to that polynomial. Likewise, over here, for this polynomial, we have 5 complex roots. Only one of them is real. There's only one real fifth root of 1. Okay, the other 4 fifth roots are imaginary. And what's the deal with this guy and this guy? These two imaginary roots form a pair of what? Remember, here's the real axis. Here's the imaginary axis. These two guys form a pair of complex conjugates. Remember that rule? If you have a polynomial with real coefficients, okay, then if one complex number is a 0, then so is its complex conjugate. A real number is its own complex conjugate, right? Again, complex conjugate pair over here. So the 5 fifth roots of 1, which correspond to the 5 complex zeros or roots for this polynomial, they correspond to this one real value, this one real fifth root, and these two pairs of complex conjugate pairs. Really lovely, really, really lovely, right? And in general, if you consider more generally, like, let's consider this over here. Consider solving this. Solve z to the fourth equals 16i. Or you can subtract 16i from both sides. Z to the fourth minus 16i equals 0. Now, this guy does not have all real coefficients, all right? But still true that 16i has 4 complex fourth roots, right? It has 4 complex fourth roots, 5 complex fifth roots, and so forth. That's still true. And it turns out that if you work out the 4 complex fourth roots of 16i, by the way, they're all 2 units away from the pole or origin. Once again, these 4 fourth roots of 16i form the corners of a square. But the complex conjugate rule doesn't work anymore because 16i or negative 16i, that's not a real coefficient. So we're not getting the complex conjugate pairs like we did before, but we're still getting the corners of a square. Likewise, the 5 fifth roots of 16i will form the corners of a regular pentagon. Okay, in general, the n-complex nth roots for any non-zero complex number will form the corners of a regular angon. Whoops. Okay, like it could be a regular pentagon, right? It could be a regular pentagon. For sixth roots, it'll be a regular hexagon, and so forth. So that's all pretty cool. But that won't be on your homework or exams. It's cool stuff, though, this rotational symmetry.